Today we're going to talk about universal coefficient theorem for cohomology with a view towards algebraic topology. Now let's see be a chain complex, for example a cellular complex, simplicial complex, singular complex. Our goal is to relate the homology groups of C with the cohomology groups of C. Wait, there's something weird about that sentence. Isn't homology only defined for cochain complex? What do we mean by homology of a chain complex? Well, given a chain complex C, there is a natural cochain complex induced from it. It's obtained by dualizing all the chain groups in C. What are these duals, you might ask? Well, they're just the group of homomorphism from the chains to some fixed group G. So, instead of saying the homology of C, we should have said the homology of C with coefficient in some group G. That's what the coefficient part of this name stands for. Okay, now we know the definition of these groups, but what about these maps? What are these maps? Well, they're just going to be the dual of these boundary maps here. In other words, they are going to be pullback map. Let us explain. Say we have a cochain F from Cn to G. Then the image of F under this coboundary map, it's going to be the pullback of F under this boundary map. In other words, it's going to be this n+1 cochain. In other words, the value of boundary of F on any n+1 chain is equal to the value of F on the boundary of that n+1 chain. Thus, this defines a cochain complex dual to C, and the cohomology group of C with coefficient in G is just defined to be the cohomology of that dual complex. A natural question then arises. What is the relationship between this homology group and this cohomology group? Our first guess is probably, maybe they're dual. That is, maybe this cohomology group is just going to be isomorphic to the group of homomorphism from this homology group to G. If that were true, that would be so elegant. We could just say the cohomology groups of the dual chain complex is going to be isomorphic to the dual of the homology groups of the chain complex. But unfortunately, not all dreams come true, and this turns out not to be true in general. To see how this might fail, let's have a look at the following chain complex. Now, let's take its dual by applying the following functor. That is, here we're taking G to be Z. Observe that hom ZZ is just Z. So we have the following dual cochain complex. Let's check that this does not hold for n equals to 2. Let's compute the homology groups of the two cycles. It's a quotient of the kernel of multiplication by 2 map, which is just 0, so this H2 is just 0. Now, let's compute the second cohomology group. It's gonna be the kernel of this multiplication by 0 map, which is just Z, and then quotient out by the image of this multiplication by 2 map, which is just 2Z. So we see that these groups are indeed not the same. But don't worry, not all is lost. Even though these aren't generally the same, there's a natural surjection from this group to this group. On top of that, we even know its kernel. Moreover, this short exact sequence splits. So we can actually express this cohomology group as a direct sum of this axt factor with the dual of the homology group. This then allows us to relate the cohomology group with the homology group. Now, if we look back at our previous example, and then compare the homology of this chain C with the cohomology of its dual cochain, then we see that these homology and cohomology groups are dual in degree 0, 1, and 3. The reason is that because in those cases, this term vanishes. More generally, this term here vanishes when this n-1 homology group is free or 0. And when this vanishes, then the homology group and the cohomology group are going to be dual. So for example, because H0 is free, therefore, for n equals to 1, this term vanishes. So we have that in this case, the one homology group and the one cohomology group are going to be dual. Now for n equals to 2, observe that H1 is torsion. That is why in degree 2, these are not dual. Now it turns out that in general X of Z mod NZ, comma G is going to be isomorphic to G mod NG. Using that, we see that the cohomology group in degree 2 is just going to be Z mod 2Z direct sum with 0. And that's why it's Z mod 2Z in degree 2. As you must have probably figured out, this statement that we were using, or more precisely, the fact that this short exact sequence splits, is the content of the universal coefficient theorem for cohomology. Coming up next, we're gonna define all the maps in this sequence, and then we're gonna prove the full theorem.